Bonjour.
Good morning, everyone. Bonjour.
Bonjour, Professor Sharavi. Bonjour, Professor Gunesh. Can you hear me?
Bonjour, Mohamed. Bonjour, Matt.
Good morning, Gunesh.
Good morning.
Can you hear me loud and clear?
Yes, perfect.
Okay, I'm just in the meantime, I'm admitting people to the room. So welcome everyone. We had a very nice tour around the world since the beginning of this workshop. We started from Greece, then jump into Belgium, and then United States, and welcome back home. Now we are in Montreal, hosting Professor Kevu. Oh, Professor Kevu just here. Bonjour, Professor Kevu.
Hello. Good morning.
Oh.
Or good afternoon. I don't know whether people have joined us.
Yeah, I guess
Hello.
so.
Good morning. Morning, Kay.
Good morning. Good morning.
And just a few words before handing over the microphone to the chair of this workshop, Professor Gunesh Karabulut-Kurt. This is the fourth session. I'm just mixing up English with French sometimes. Session with Professor Kevu on the Terahertz days. It has been a very successful event so far, and just to give an idea to the participants, please feel free to drop your message or question in the chat box, and we will accommodate all of them at the end of session in Q&A session. And so apart from this, just want to double check the screen sharing functionality with our co-hosts. Professor Gunesh, can you please let me know if you have access to?
Yes, Matthew, I have access.
And
no
would
problem.
you like to share a screen to give introduction on the workshop?
Okay, let me start then. Can you see my screen?
Yes, yes.
Yeah.
All right. So welcome everybody to the fourth session of the Terahertz days. My name is Gunesh Karabulut-Kurt. I am with Polytechnic Montreal, and I am the chair of this workshop, jointly co-hosted with IEEE Young Professionals Montreal. We are part of Polygram Research Center, and today it will be my pleasure to invite our director to give the talk. And the Polygram Research Center has been established in 1992 and has been very active in millimeter wave and terahertz bands. The use of terahertz bands has a lot of potential in terms of the data rates and the applications towards the sixth generation, and it is becoming real, and that is our motivation within the organization of these talks. Our first speaker was Professor Angeliki Alexiou from University of Piraeus in Greece. Our second presenter was Professor Christophe Graye from Université Catholique de Leuven in Belgium. Our third presenter was Mona Jarahi from University of California, Los Angeles. And we are happy to host our fourth presenter, Professor Kevu, with his presentation on accurate material characterization over terahertz frequency range. Now I have prepared a short biography of Professor Kevu, but it's still a mouthful. We are very happy to have him here. He has graduated over perhaps 150 or close to 200 students with over 50 patents, 1,400 papers. It's like it's an amazing. We feel fortunate to be working with Professor Kevu, and I am personally looking forward to his talk. Thanks a lot, Kay, for accepting our invitation and giving this talk. Let me stop screen share and please go ahead, Kay. Thank you.
Well, thank you very much, Gunesh, for the nice introduction. And also, I want to thank Mansour and IEEE, the Young Professional Montreal for this, also the invitation to the arrangement. And well, it's great to be here to talking about the part of the work going on right now at the L'École Polytechnique, of course, within the Polygram Research Center. And so this is a great opportunity to talk about a little bit also the future directions eventually in this in terahertz domain. Okay, let me now open up why this okay the share. It sounds like I cannot share. I cannot get into the host. There's a host disabled participant screen.
Just a second, Professor. I'm going to the co-host. You should be able to do it right now.
Oh yeah. Okay, now it's getting better. Yeah, no, it's okay. Good, great. Thanks a lot. So the okay. Now let's get into. So can you see my screen? And
yes.
Okay, great. So well, I'm going to talk about today the interesting topic. Actually, it should be one of the most important topic for the terahertz development is related to the accurate material characterizations. Okay, how we can make the parameter extractions from any materials operating over terahertz frequency range. So, well, I think first of all, I want to thank the number of people who contribute to this work, and of course, those people actually has been instrumental to setting up of this work and the development of this research program, and with lots of nice results in the end. So I just want to thank of them, thank them. But of course, I will not talk about detail of this own research there. So today I'm going to spend roughly 1 hour to talk about this accurate terahertz, the material, the measurements and the characterizations. The fundamental issue is really let's start with terahertz technology. Then I will talk about the state of art, the MHz-through-THz material characterizations, and also, on that particular aspect, I'll talk about today's all different techniques, okay, different technique which has been used, and also some of them actually still very popular at a low frequency, but may be questionable or could be present some problem at high frequency such as terahertz. And we'll talk about terahertz quasi-optic, the mirror measurement system. Actually, talk about mirror here. We'll talk about the ellipticoidal or the parabolical the system, and we'll talk about also the quasi-optic lens measurement system. The lens actually is transparent. Beam from one end to other side. So, which is different from mirror. Mirror usually reflective type of the measurement system. So and then we'll talk about also some of the nice results we have obtained at the Polygram Research Center, and of course conclude my talk with them. So let's start with the terahertz technology. Well, terahertz technology has been in the community since many years. And why right now it's become popular because of the 6G, okay? Well, actually 6G is not just talking about the terahertz. 6G talk about the full bands, okay? We talk about the any bands, anywhere, anytime, and any services eventually, okay? So that's really the core part of 6G, but definitely the most challenging the search within 6G is really related to the terahertz frequency bands, how we can explore and develop the 6G technologies. So that's something which most of people right now invest. Spend a lot of time on the high frequency bands such as sub-terahertz up to the few terahertz, the frequency range. So, of course, if you look into the terahertz frequencies, there's a lot of issue there, and at the low frequency, we don't fear any problem related to the transmission, the impact, particularly transmission loss aspect. But over terahertz frequency range, you can see the transmission become extremely dispersive. in terms of the loss and also eventually phase variations. It's because of at different frequency range, you may end up with different transmission loss, and which can be caused by different environmental factors such as water vapor, water, the molecules, and oxygen, and anything you can see in our our environment. So this really these two curves show that in a very dry the weather conditions, and also compared to the weight conditions, you can see you have very significant difference here between the significant difference of transmission over this the terahertz frequency range. So that's really the problem for the terahertz system, particularly for the long distance transmission. But even for the short distance, such as our laboratory based measurement technique, and actually we have to also pay attention to this the absorption effects due to the water, the vapor, and also the oxygens. So I will show you some of the interesting results we measured in our own lab. So this definitely talk about really the cost issue. Of course, at terahertz, everybody know that it become more expensive than the low frequency, and also the fabrication become a little bit more complicated. Particularly, the information about the materials is not really known to many people, and so that's why the parametric instructions of those many materials at the terahertz frequency range become really the important for any further development. Okay, because without knowledge on the materials, for example, if I give you a silicon wafer or the gallium arsenide wafer, indium phosphide wafer, if you don't know the exact loss tangent and also the permittivity values, you cannot really do a good design, because there's a lot of the fundamental issue which has to be solved before the design of those integrated circuits or any other things. So, but today for the terahertz technology, there's two I will say the major efforts. One from the electronic side, they try to build up the electronics-based terahertz systems. Other side is photonics. So that's really because terahertz frequency range is there's a lot of the fundamental issues. For example, the power generations, signal generations, and also the fabrication issues also become problems. So there are lots of things involved in the terahertz frequency, the system design. So one of the things that I just want to tell you that the most important definitely is the material. Okay, the information about the material, such as loss index, mechanical, the properties, and also the tolerance issue. For example, when we design a waveguide, if we want to use dielectric waveguide, and how we know the materials information, so on, those kind of things. So regarding terahertz technology, today is the most important. Also, another important, in addition to the material information over terahertz frequency range, another most important the difficulties, I will say it's really the power generation at terahertz frequency range. So that's why this is the chart tell you that we usually today we talk about only the milliwatt at the 1 terahertz frequency range. Beyond the 1 milliwatt has become more and more difficult and also become more expensive. So I will not go through this, because this is really the interesting discussion, which actually I have another presentations eventually we'll talk about a little bit later in the future. And also based on the new materials, new process, we may end up with new the IC design for terahertz. In addition to the traditional silicon, for example, or the gallium arsenide or gallium indium phosphide, or even other technologies. So the terahertz depended on really the different type of the semiconductor technology, in addition to today's some interesting emerging the new materials. So definitely today the majority of this terahertz development is really related to the integration. Okay, how we develop the integrated circuits, different type of integrated systems, so on, and for different the functionalities such as communication, sensing, and imaging. So I will skip this part, just focus on today's the main topics which I want to address today here. So well, before talking about the quasi-optic measurement system, I will go through together with you all the different state-of-the-art the MHz-through-THz the measurement technique for material parametric extractions. Those material calculation techniques actually can be classified into different approach, okay, different the categories. By the way, the material characterizations or parametric extractions from measurements actually is related to the inverse problem. It's not a direct problem. So which means that through the measurements, how we can extract the materials information in terms of the complex permittivities, for example. Of course, the loss tangent is involved here as a function of frequency or even as a function of geometric dimensions. So this is the inverse problem. Actually, inverse problems actually become much more involved in the in not only just in the measurements, also in the calculations. So I believe that for the computational electromagnetics, actually inverse problem has been always the most difficult part. Okay, so this means that we should not only just do the accurate measurements, but also how we can make the accurate material characterizations through these inverse problems in connection of the measurements. So here you can see that those different measurement techniques actually through the different I could consider the so-called test setup. For example, coaxial line technique, or planar transmission line technique, waveguide technique, or free space quasi-optic technique. All those techniques actually are designed to support such accurate material measurement, material calculations through the direct measurement technique. Okay, so there's a different, of course, if you look into this kind of the different the technique here, there's a lot of the formulations, the computational electromagnetism involved, and also there's different interesting the so-called the parametric extraction techniques through the mapping, for example, through different approach. But among those techniques here, I would say that there's three different type, which actually very common for us. One is called the reflection type. Okay, reflection type is actually the single port. For example, the early time HP company, right now we call it Keysight. The first model proposed by HP was the so-called coaxial end open end, the coaxial open end technique for the low frequency up to, I think, up to the 18 gigahertz. So that was very popular, actually still very popular today for the so-called low frequency, the quick, the material characterizations. And so this is a so-called reflection. Of course, reflection can be also developed through the other techniques such as waveguide or the free space, the approach. And the transmission is a two-port technique. Okay, transmission two-port technique. Among them, there's different type. Okay, you can put the material under test inside of the waveguide or coaxial line. The material under test actually subject to the transmission. Okay, through the so wave passing through those materials while subject to the phase amplitude change. Part of the material, part of the waves will be reflected back. Okay, so through the transmission, we are able to extract the parameters. But sometimes we need to combine reflection and transmission both information to extract accurately the material under test. Okay, extracted the materials parameters under test. So we developed also many years ago, actually in 1995, a very interesting technique called the transmission discontinuity technique to make the very interesting mapping between the S parameters, measured, and the material parameters, complex permittivity. So this mapping actually was very popular. Now it become interesting for many of these accurate measurements also. So definitely reflection, transmission are both very good for the broadband the measurements. Okay, broadband material calculations. However, for very accurate measurements, sometimes we have to resort to the resonator technique. Resonator technique is definitely the narrow band, usually the only point frequency. So, but because of the resonance, so we are able to extract very accurately the material information at the specific frequency points. So the different technique used here, of course, I will not go through this. Today, I will highlight more on the transmission reflection type structures. So the feature of this technique actually can be summarized through this. I will not discuss this too much because there's so many interesting papers, techniques developed in connection with the material characterizations. I just want to highlight one point here. For the free space quasi-optic technique here, there's a emerging radar technique which has been recently developed, deployed to do the so-called remote material characterizations. This is very interesting new techniques, and I will probably show you a few references here. So let's look into the free space measurements to start. Okay, let me show you one example which was developed by many other people here. So well, in the past, the people developed these different type of transmission of free space quasi-optic measurements based on the time domain spectroscopy, for example, based on the frequency transfer spectroscopy, different type of technique which has been used. But the problem is that this time domain spectroscopy or frequency transfer spectroscopy is actually, the problem is related to the dynamic range. The dynamic range is not very good, and also frequency resolution is very, very poor. If you think about the time domain spectroscopy, which actually has been very popular in terahertz domain, and the frequency resolution has become problem, particularly when you talk about very highly accurate material parameter extractions. I would say particularly for the low loss materials, TDS, time domain spectroscopy, definitely will fail to extract those informations. Okay, so that's why this is people looking to other alternative solutions. One of them really related to the free space or quasi-optic measurements based on VNA or PNA today. VNA actually present very good dynamic range, and also very good, excellent, I would say, this so-called frequency resolutions. And this is important for the terahertz, the measurements or parametric extraction, because we see that over certain frequency range, you have very strong resonance or the variation. So that's why the parametric extractions with the fine frequency resolution become critical. So this is and also, of course, most of the IC or system development at terahertz frequency range will require low loss materials. So the loss tangent usually for those materials are pretty low. That's why we need to have the very low loss, accurate low loss material characterizations. So Well, if you look into this TDS technique, okay, but if without thinking about this dynamic range problem, frequency resolution problem, but this quasi-optical approach actually has been very good for the for if you look at this, okay, this is a very nice illustration of the the how we do the perform the measurements, and actually you have the single mirror or single single mirror system here, for example. Okay, you have the two mirror system here, and you have also the four mirror system here. So the four mirror system actually provide more flexibility in terms of the size of the the material under test, and also you can create a very fine beam west to spot specific position at this material under test. In this case, we shall be able to really extract the materials at the different spots, and eventually we can create the so-called the imaging of the materials in terms of the permittivity or complex permittivity and so on. So that's interesting. There's different published paper there. Okay, I will not go through this detail. And this is really free space, the measurement through the lens technique. As I said, the lens is transparent. You have the antenna horn here. And this is usually the horn can be managed through the corrugated technique, such as the create Gaussian beams. And then you can use, of course, the Lomo horns, but Lomo horn actually the efficiency is not so good. And at the same time, you can see that the beam actually is transformation. Okay, so from one side to another side, and this is so you can create a similar approach as this mirror technique, and to do the two-port transmission measurements here. So that's different. There's a different paper published on these topics. And of course, there's other techniques such as the on wafer measurements. On wafer measurements, we can do the, for example, the specific material such as the biological cells, which is very difficult to do the quasi-optic measurement. You need hosting material there. And so the on wafer measurements, they become interesting for this biomedical technique, biomedical materials. So actually, in our group, together with our colleagues, we are working right now on the how to extract the biological cell over terahertz frequency range. So okay, this show you some emerging technique today. This is based on radar to do the remote terahertz, the millimeter wave material characterizations. This is interesting because I said this can be done over long distance, and also completely non-destructive because the material can stay intact, and you just do it's actually the radar technique. So radar technique actually really looks like an open-end technique. Okay, just but now the open-end coaxial line now replaced by radar. That's it. So, but of course, the signal processing will get much more involved in this radar technique. Okay, I will not go through detail of that. For those who are interested in reading the papers, okay, at least a few of my colleagues work here. And there's another interesting technique based on the optic approach that we called the so-called the interferometric technique. Okay, so this technique actually becomes also the very good. When we talk about this, particularly when you're looking at a very thin film. So when you have very thin film, the block structures, okay, like thin film or the material solid-state blocks, you can do the nice work here, and of course. This, for example, if you have beam come out here, you have a parabolic beam, mirrors, and then the beam come out of here. Then the incident into this through this this actually is a beam splitter here, and then through the another prism and reflect back, and then the this actually goes through directly to this path, but this beam actually split here the two paths. Okay, one path as a reference, another continue this. Okay, so that's why so it's actually interferometric technique to do the detection. So it's like the use same beam, but they split in two parts, and actually they combine again at the receiver side. So this is the one of the also the interesting technique. Of course, you can do other things through the other approach. So I actually I don't know why this is the I'm actually part of my screen is blocked by this. I would because I don't know why this is all. Let me use the. I have to use the maybe laser pointer. Okay, I couldn't find laser pointer here. So now so this is the another technique, of course, use the, as I said, it's kind of the similar as the lens-based technique. Actually, it's a straight transmission to do the material calculations. But this technique actually has some problem because you need a very good planar wave, and so the distance actually is limited here, and so this type of the measurements we need to be careful to do some the accurate parameter extractions. So, but this technique is very straightforward, and can be done in in a laboratory in a small space actually. So, well, I couldn't see this screen on the upper portions. I don't know how we can do this because this is the this is really the annoying portion of this. It's covered by I don't know how the this is it's a problem. Okay, because the block portion of a part of my slides. I don't know why this is happened.
We can see the slide clearly, Kay. I don't know.
Yeah, but I there's a bar actually. The bar actually, there's a block. Okay, now it's not, and I just do that something here. Okay, so the I know why. Could you because somebody getting each time admit. So since I'm assigned a co-host, so automatically I become the bar appear. It's like reminding me constantly, So could you remove the put me as not the co-host? That will be great, better actually. So yeah. When the people join, the bar appear. So the half of the slide is gone. So right away. Okay. So now let's look into the material, how we do the parameter extractions. Okay, if you look into the now let's forget first for the permeability aspect. Let's think about only complex permittivity. So complex permittivity, if you write a generalized term, so we have these formulations. Okay, so the relative permittivity actually can be expressed as a complex term. For example, epsilon r prime. But also epsilon r double prime plus the conductivity. But for most of these low loss materials, the epsilon r double prime doesn't exist, okay, or it's all negligible, because this means that this is a frequency independent epsilon r double prime, usually over the certain frequency range, of course. But the conductivity represents a leakage due to the imperfection of the materials or the crystalline the structures. So in this case, you see that the loss tangent actually will be described very well, this complex term as a whole. So the dielectric this is a frequency independent portion of the loss tangent. Actually, usually it's negligible. We are not really considered too much. But as the generalized measurement term, we can consider as the whole, because we measure, and always we measure from input to output. We don't care about what's inside. So, but if you look into the liquid structures, like liquid materials, eventually you end up with some of this interesting, double prime. So, but we'll not discuss this the material property here itself, but we will just look at how we make the accurate loss tangent, particularly in the low loss material, low loss cases here, how we extract this loss tangent. Okay, so but over the frequency range, you see the different behaviors, and at the low frequency, actually the for liquid structure a little bit more complicated, but for all the solid structures, solid materials, the material property actually very stable at the low frequency, but only as the frequency goes up, the material property, including the real part, could be affected because of this, the material structures, actually the certain kind of the dimensionality here. So dimensionality will be seen more and more, inferential actually, as the frequency goes up because the wavelengths become shorter. So that's very natural explanation for that. So at the terahertz frequency range, for example, you can see, as I said earlier, that you can see the dry weather and the wet weather. You had complete different the responses here. So I want to just highlight one point here is 180 gigahertz. 180 gigahertz. If you use a dry, the laboratory environment, you don't see that at all, for example. However, in the wet, the conditions such as the water molecule, conditions, okay, in the wet weather condition, wet weather environment, you can see you have a strong absorption here. So which means that in our laboratory, for example, if we make the measurement at 180 gigahertz, if that day you have extremely wet, okay, extremely, it's a rainy day, for example, I think you should be careful because eventually you got some problem here at 180 gigahertz, okay? So that's just to let you know some of the things we have to pay attention to. And also again, that's trouble for me, anybody getting into this room right now, all the half of these slides the blocked. Okay, I think, okay, so if you look into the this kind of the spectral responses here, over certain frequency range, of course, you have large attenuation naturally. So for this kind of the frequency points, the measurement should be done carefully, and even with a short distance. Okay, so the distance is very short distance. The you have to be also careful. Even when we talk about like a few centimeter, you have to also see the difference here. So. Okay, I just show you here, for example, at 180 gigahertz range. Okay, so that's a little bit more than 180 gigahertz. So you can see that if different humidity, you can see you have different absorptions for the transmission here. So that's why it's very delicate to make a measurement. And also at a different frequency, for example, naturally, even for a given temperature and humidity, you have also very strong absorption due to the oxygen and so on. So that's the natural absorptions, which also affected both by the oxygen and also the weather conditions. So now let's spend time to talk about a little bit the quasi-optic technique we have developed, and also just give you an overview how we can achieve the accurate material characterizations. Okay, So this is typical two-port transmission measurements through the quasi-optic parabolic mirrors. So the beam actually can come out of PNA or VNA. Okay, here we use PNA, XN, the 5245A. And so we go through the Virginia diode, the extenders, okay, which convert to the, you know, the 140, actually here 220, and actually beyond. So the horn could be replaced by corrugated horns usually, because we need to create a very good the Gaussian beam here. So the beam come out of this horn and they hit this these mirrors reflected towards the horizontal directions. You have the this usually here you have very good high quality planar waves, okay, but the large areas, okay. So then you'll be the beam come if the beam goes through this you know the material under test, then will come in to the second mirrors, of course, reflect back. You can see this path here will be complete two-port measurement path for the VNA or PNA. But the how many if you don't use material under test or the lawless material under test, then you need to have the majority of the power coming back to this receiving port. Of course, some beam may reflect back to the transmitting port. Okay, so that's why this is important. But for this kind of so this is important to do the so-called the system efficiency the measurement prior to the actual measurements. So we want to do for terahertz, one of the most important things that we need to do is to create a very high efficiency, low loss transmissions, okay? And for this quasi-optic free space measurements. So which means all the power should be not wasted in the space. Everything should coming back or the transmit to the system. And so for this kind of the generalized material, for example, if you consider permeability, permittivity, for this the planar wave transmission over this low loss materials, you can have the reflection coefficients here or transmission through this L. L is the thickness of the material under test, and of course you can develop also transmission reflection coefficients through the formula as generalized. The term here, okay. I will not go through this detail here, but one of the most important technique which has been used for in the community actually is called the multi-reflection calculations. But unfortunately, multi-reflection technique was not very well developed for the you know thin the materials because well, most of people don't pay attention to how to extract the extremely low loss loss tangent information. Okay, so that's today actually want to highlight this research in our group here. So, well, the multi-reflection calculation actually is based on the physical you know the phenomena here. For example, if one wave coming here. So the wave coming here, of course, will be, you know, they will first of all encounter the first interface here. So this the boundary condition can be characterized by the you know the tau 1, and they will reflect it back, and also part of the energy will be transmitted into the material under test, and then will be encounter second interface from material to the air. Will be reflect back here again. Part of energy will continue to transmit, you know, continue to propagate. So this reflection continue to reflect back here, and it will go through the second reflections here and also transmission. So you can see the reflection, transmission, reflection, transmission. So the multi-reflection, the calculation here. So we can use this technique to develop the very standard the multi-reflection using the linear superpositions here, okay? Because all the reflection transmission here actually was subject to the linear superpositions. So we can get the total transmission and the reflections through this formula. Okay, this is a very standard formula. And so, but this AB, for the B here, the B is only talk about these blocks here, but the A talk about it here. Of course, A is in the free space air regions. So we assume that there's a perfect match at the end of this the measurements. So A1, A22 becomes 0, and so on. So so the formula can be developed through this very simple the equations. And actually, we can use a signal flow chart to describe this, but I will not go through a detail of that. Just to let you know that you have two scenarios here. One scenario is that we assume that the material under test replaced by the air. Usually, this should be done prior to the actual measurements of the materials. Okay, under test. So you do the measurements first with air. And so this is like a calibration process, but this calibration is actually I could consider a second calibration, because you have system calibration, but this calibration is related to the specific measurement conditions here. So these two measurements, procedures generate a number of equations. Okay, I will not go through this. You can see this. These S parameters basically tell you a story about the port-to-port measurement from the VNA. Okay, so VNA, and you have air, the first conditions. You have the second, the measurements under material tests here. So this is correspond to the air and the materials, of course, under two conditions here. So we can formulate those equations. But of course, as I said, we only consider the permittivity. If we consider only permittivity, actually the situation becomes a little bit simple, because we can do we just need to consider only the transmission aspect. We don't need to consider the reflection aspect. But if you have the permeability presence, in this case we have to consider both transmission and reflections. Okay. So actually, because transmission reflection give you more equations. So because of the permeability is another additional unknown the parameters. So of course you need more equations to do calculations. Okay, that's a very simple way to explain that. So the detail of that actually involves several things. First of all, we basically use perturbation technique. What do we do? That first of all, we assume that all those previous equations is assumed that first of all, even under the material under test in the computation domain, we assume those equations without loss. First of all, with lossless the calculations. This lossless calculation can be denoted by this gamma. You have the subscript 0 here. 0. This T0 means that the lossless material test. Actually, it's not test, the computation aspect. Then you end up with the loss, the actual measurements. Okay, so those actually S21 M materials, S21 air is actually the port-to-port measurement results. Okay, so those results and all those equations, other part of this loss tangent equations come from the computational model. Okay, it's a model. It's a multi-reflection models. So you see these loss tangent parameter extractions actually come from the combined analytical models together with the measurement results. Okay, so this measurement results is explicit. So in this case we can develop very simple the analytical equations, which allows us to extract the low loss the loss tangent. Okay, low loss materials loss tangent. Okay. So this is a very interesting solutions which give us very, highly accurate parameters. I will show a little bit later on. And of course, this is actually these procedures actually can be tested through the so-called multiple level of the calculations. We call it the ergodic calculations. And so these procedures actually iterative, and such that finally we're able to get to the final results through this process. Okay, so I will not go through this detail that because these equations involve itself, it's the nonlinear process. It's a nonlinear equation. That's why we have to go through this iterative, like a searching for solutions. Okay, so this is detail of that loss tangent resolution. Okay, why we develop the loss tangent resolution technique here? Because as I said, we consider low loss, which means that extremely the loss tangent value is very smaller. Okay, but because of this, the smaller values, how we can get to the very accurate the resolution, like a frequency resolution, for example. Okay, we talk about here loss tangent resolution. Loss tangent resolution means that how much we can go to get to the accurate parametric extractions in terms of loss tangent for loss materials. Okay, that's the most important information we want to answer. And so again, that's okay. So now let's look into this. If you look into this, okay, I will not go through the detail of that. It's a more or less, for example, we in the analytical formulas, for the material parts, we develop the transmission equations from port 1 from the interface 1 to interface 2, and also for low loss materials. Okay, those equations we developed. This ratio we called R. This ratio gave these equations. Okay, and those equations involve the loss tangent values. And of course, this for the materials in the real materials, okay, we can also develop the material aspects. Okay, so this formula, it's actually similar to this one, but of course we developed in the expanded way, for example. Okay, so this I will not discuss the detail of this expanded formula, but this formula, because this ratio should be smaller than 1. Why? Okay, you have the actual for example, from the interface for the giving materials blocks, for example, from interface 1 to 2 transmissions versus the 1 to 2 transmission without loss. Definitely without loss give you better results. So in this case, this ratio should be smaller than 1. Okay, so that's very natural. So this ratio smaller than 1 is condition, actually physical conditions. And then from there, we are able to develop these ratios, and this ratio gave these formulas, and these formulas gave us finally give this so-called the loss tangent should be larger than these terms. These terms associated with the so-called the variation of the S parameters. Okay, here, but I will show you some of these interesting results. So the equations, okay, these expressions, this loss tangent, should be larger than this one. We called the loss tangent resolution. Okay, so this was developed for first time in our laboratory. So to quantify how much we can get how accurate we can get for the loss tangent parametric extractions. Okay, so which means that we need to develop we should be able to develop the test setup which allows us to make the parametric extractions, and which should be the loss tangent value should be larger than these values. Otherwise, the resolution loss tangent the parametric extraction is not correct enough. So that's why this gives us a very good insurance about the accuracy of the loss tangent. Okay, I have to hide the floating bar here again. So, for example, okay, this loss tangent here for different materials, okay, you can see that for these values, for example, is a very large ratios, and these ratios mean that if your loss tangent smaller than these values, definitely you cannot get the accurate measurement results, because you don't, the loss tangent resolution cannot be satisfied, okay? Because you can only measure the high loss materials larger than these values, okay? So these values come from the calculations, okay? And this is particularly important, for example, for these multi-reflection models, usually it's very good, okay? So for multi-reflection, the models is very good for thin substrate or thin layer structures, okay? For thin, the substrate material test. But for thicker substrate, for thicker wafer, for example, we don't need to use the multi-reflection models, okay, in this case, because of the, there's no need for that. So in this case, we can simplify analysis. Actually, for loss tangent resolutions, we developed two formulas. One is we call the multi-reflection model based the loss tangent resolutions. Another is the absence, okay, as a single transmission reflections to which allows us to also make the loss tangent resolutions. So in this case, we are able to get the modified formula for the loss tangent resolution calculations. Okay, there's two different formula, but this both formula can give us a very good predictions about accuracy of your the loss tangent extractions. And also regarding Gaussian beam design, of course, this is well known in the optical domain, but in the quasi-optic fields, of course, one of the most important thing that over the large frequency bands, you have to create a very high efficiency the Gaussian beam generations. Particularly, we have to pay attention to the beam waste regions. Okay, and so this is a formula we talk about how the beam evolve as a distance. Let's say as a observation, the point of observation, goes away with respect to the original point, which actually the beam waste located omega 0 here. So the beam expansion or beam beam width enlargement can be formulated by this formula as a function of the point of observations. ZC actually is the cofocal distance point. Okay, so so this is the so for example, in this case, one of the problem in our measurement setup, first of all, we need to create a very high quality Gaussian beam coming from the waveguide sections here. So there's the waveguide section provide usually the normal horns, but the horns cannot be used for the generate high quality the broadband the so-called Gaussian beams. Okay, so Gaussian beams should be generated by the corrugated horns. Usually corrugated horns should be designed specifically for this kind of quasi-optic technique for a large bandwidth, because for the quasi-optic measurement technique, we need to pay attention to aspects. First of all, from the horn port to horn port, you need to have the very good stable optic path over the broadband frequency range, which means independent frequency independent optic path. This is one of the first important information you have to pay attention in regarding the measurement setup. Second thing that you need to develop the corrugated horns, which allows you to have the very smooth the beam waste variation as a frequency change, which means it's like elastic way. So in this case, it's becoming frequency independent. The total path from the port to port measurements is become the frequency independent. The optic path, which means optic path become frequency independent. Let's say this way. So from the home port to home port, you can use optical ray transfer metrics to do some optical path analysis. So this is it's quite similar to the microwave ABCD metrics, but the optical beam propagation approach here. So this F is a focal length. Okay, so you see that, okay, D, of course, let's go. D is all the geometrical dimensions, D1, D2 here, D2 is a half D here, so on, so on. And D2 versus D1, you have the K ratio here. Usually, we set up in most of our analysis K equal to 2, which means you have the half distance of this distance. Okay, so from this formula, we can get to this ABCD total metrics, and to develop this so-called frequency independent optic path, you need to set up the B equal to 0. The B is this one. The B equal to 0 means that you create the frequency independent path. And in this case, you have two scenarios here. For parabolic mirrors, means it's the focal distance should be equal to D1 actually. Or in the ellipsoidal the mirror systems, the F actually be associated with D1 and D2 values. Okay, so this focal distance actually is equal to this. So this gives us some restrictions regarding this how put the distance. So the system cannot be put arbitrarily. And actually, there's certain conditions which should be satisfied here. So this is of course you can use this to create different analysis for the optic transmission quality here. And so let's look at the ellipticozoidal mirror measurement of the system development here. For example, in this case, you have to consider there's a certain certain value you have to pay attention to, because in the measurement setup you have certain thickness. The thickness is that it doesn't mean that you'll be coincident with the very central point, and particularly in this ellipsoidal mirror system, you have you reach the so-called the output, the optimized the beam width, which actually is not necessarily coincident with your the central points, which means you wanted the middle points here. So these usually they give a distance so-called the delta here. So beam actually could be distorted when you put the actual the sample under test here. So that a certain kind of consideration should be made for this kind of measurement setup. Okay, so this delta actually is a very tricky for the measurement. We want to delta as small as possible to make sure that the measurement can be accurate. But at the same time, this gave us also restriction about this so-called how much the thickness of the material under test. Okay. Of course, we consider thickness is those kind of like thin film, thick film type of structures. And for the parabolic mirrors, actually give us a much better solutions in this case, because in this case you have the planar the beam propagation between the mirrors here. So the D naturally equal to 0 here, or delta equal to 0. In this case, you can create a very good arbitrary unlimited thickness measurements. So this type of the parabolic system actually adopted in our laboratory. We like this measurements better than that. But on the other hand, the elliptical measurements, I go back to this. Okay, I'm sorry. Let's go back to this. You can see that you can create a very fine beam here. If you the very fine beam here actually can be used for the specific spots measurement. For example, if you have a thin film which you want to test, the thin film will have the uniformity of this over the entire structures. In this case, what you want to do is you want to do the so-called imaging. For example, you want to create if you let's say make your thin film move around here, you're able to see uniformity of the film through the measurements. Okay, at the same time you can create imaging. So the quasi-optical based ellipticozoidal mirror system actually can be used to create an imaging system, for example. Okay, this is very convenient here. Okay, so in addition, to be able to do an even better job let's say for imaging or for the small spots, high resolution measurements. In this case, we shall be able to do, for example, to create a four-mirror system. But because I said we can use ellipsoidal system, but ellipsoidal system has some kind of the problem associated with this value value delta. I'm sorry, delta, means that you have the so-called the optimized spots and the beam west and the actual beam west. I have this delta value here. But the parabolic system actually give you much better solutions. And actually, you can use a four-mirror system, such as a four-mirror system, to create a very narrow beam to focus a beam in the middle point. In this case, you can have the you can also use the four-parabolic mirror system to create imaging, as I said, imaging, or the to check the uniformity, for example, of the material under test. So, so this is a comparison of the design characteristics, okay, of the different systems. We have ellipsoidal mirrors. Okay, as I said, the delta is a problem. As I said here, you can value here, you can see the value here. But the parabolic system actually gives you much better control of this, the beam of those specific the spots for the material under test, and also thickness can be unlimited because of this the beam and the particularly the planar wave beam here. So that's they give us advantages. Okay. So two-mirror system, usually you have to look at the quality of the Gaussian beam generations, and then usually the Gaussian beam. Okay, we look at the efficiency. Efficiency, usually Gaussian beam efficiency can be made roughly 98%. Okay, 97, 98%. And so particularly when you look at the corrugated horn antennas, okay, corrugated horn. Okay, sometimes we also call corrugated horn antennas. The Gaussian beam efficiency actually is very high, okay? But sometimes through the propagation from one port to port, usually the beam can be offset because of the alignment, also mirror conditions. So you can have some kind of the actual problem. Okay, that's also. So this is something which we have to pay attention to, okay? So for example, in this case, you can see that the beam can be slightly distorted and also can be offset a little bit because of the propagation behaviors. So the beam alignment becomes important. And so this is four-mirror beam placement in our system assessment. Of course, four beam, you have a longer distance, longer optic path, then the efficiency becomes smaller. And so usually, we can have 95%. So in any case, more than 95% is a very good system for our low loss quasi-optic path. Okay, but even for today, many of this like Gaussian efficiency we call the Gaussicity. Usually we end up roughly at 90%. Okay, so that's the most of the system developed today. Okay. So, okay, so this is the actual system set up. So the PNA, for example, port one goes to these directions, and go to with the VDI extenders, and the convert to terahertz, and then we use very specific custom-made the corrugated horns here, which cover the frequency of band of interest, and then launch the Gaussian beam here, and then you use the mirror system here, the fixed of the optic tables, and this is a sample holder. Usually, sample holders can be placed, of course, in the middle portion of the system, and then this actually can be also made mobile to make for example, the configurable. I could consider in this case. You can make the imaging, for example, test, okay? But of course, in the four-optic mirror system should be done this way. But the two-mirror system is actually large planar wave sections, okay? You cannot do that. So usually what you do is only the average value of the entire substrates, okay? So this is a 2-meter system. And so, so in terms of the corrugated Hall antenna design, I will not talk too much here, but just let you know this is very important, critical, and also very expensive design here. So we developed here actually three horn systems. With different parameters involved about the waveguide sections. Okay, you have the so-called you have to pay attention to the how this slanted section of these horns. Okay, because slanted sections actually involve the length. The length actually the larger the better, but it cannot be too large because you need to compromise. So I will show you some of these results. But here, basically, first of all, we need to determine how much the middle section of this so-called beam width we want to achieve. For example, we want to have the larger section 25.4 of the millimeter, the diameter of this beam. Okay, so in this case, we can calculate the input, which means that the input of the so-called beam width generated by this corrugated horn. Okay, so corrugated horn actually give value actually about 1.91 lambda. So this one has to be satisfied during the design of the corrugated horn. Okay, so that's the value we have to get. So this formula tells the right away story of this geometrical dimension design. So this is our horn design to achieve very nice. This is the waist plan. Okay, so this is aperture size here, and actually this aperture here. So in this case, you see that so delta actually of course delta A. I'm sorry. Here's the delta ZA here. Should be the smaller value. Okay, somebody. Okay. So the delta A here actually should be smaller than smaller the better, but actually cannot be cannot be smaller. Okay. So we have to make a compromise in terms of design here. So there's some design equations we have to consider here. Actually, these values slanted. The length actually should be measured from here to here. Is this slanted sections? It cannot. This is actually this should be small mistake here. Should be considered like this. Okay. So the based on the angles. So this is our generated WR 5.1, the corrugated horn. This is the turn loss measurements. It looks pretty good over the frequency range, except at 210 gigahertz regions, you have some trouble here. So there's some design defects in the, this is a CNC machine cannot be designed easily. Actually, it's not was not made in our laboratory because we haven't done that. Our laboratory cannot do that. Actually, with our EDM, eventually we should be able to do that. But it's very difficult to do this because of this is inner the corrugated structures. So so you can see definitely realize again supposed to be flat enough. And so, but of course, it's gradually increase as the frequency increase. That's very normal for any antennas. But on the other hand, at the 2.10 gigahertz, you have a drop here, and actually with confirmed by measurement, simulation measurement, both actually confirmed here the value. You have certain defect in the structure. We know that exactly, but because of fabrication problem defect, we made the simulation to see how it works here. Indeed, there's a measurement confirmed. There's a slight deviation, but the efficiency is still very good. You can look at the efficiency, over the frequency range of interest is quite flat. Okay, so it's about 98%. Okay, so to measure the quality of the Gaussian beam, first of all, look at we use our NSI MI system. It's a robotized quasi-optical measurement system. We look at the corrugated horn, launch the Gaussian beam to look at the beam quality at different angles. We use the 45 plane cut, 90 degree cut, 180 degree cut, different cut to see how the beam looks like. Okay, so with this 180 gigahertz the gigahertz measurement. So you can see 45 or the 135 is the same, okay, because that's the same angles. So okay, you see that the different so this is the core pole, this cross pole, all the cross pole measurements and simulation. So simulation measurements, the results actually agreed very well with the in this plot. You can see. So that's really the high quality design we have made, except that the little defects at the frequency 210 gigahertz regions. So, okay, this is the measurement setup, robotized the terahertz optic on-chip measurements. In this case, we use a horn antenna system for this corrugated horn measurement. Okay, we also measure at 140 gigahertz. You see the core pole, cross pole, the measurement simulation agree very well. Okay, except the cross pole, you have a little bit deviation, but it's okay. That's the acceptable because of the certain condition we cannot really consider in the actual measurements. Okay, this is 180 gigahertz for different conditions. Okay, so that's the well, again confirmed our measurement simulation results. So this is 220 gigahertz. You show again, this is 45 degrees, 135 degrees. The core pole, cross pole measurements still very satisfactory, even though there's some kind of beam deviation, some beam not distortion, but the beam little bit slight enlargement here, but still satisfactory. Okay, for our measurements. So we use that corrugated horn antennas. At the same time, before they do anything, before everything, we have to also make sure that we have very accurate alignment and the distance. So two types of things. One is alignment and distance. So alignment, distance can be guaranteed through the optic table, but alignment has to be done also properly because small alignment for the terahertz system measurements is very delicate. Okay, so we need to do the using laser technique to do alignment here. So this is the laser blue laser here. So this is our system test setup to do the quasi-optic. Actually, we have two. One is a 2-mirror system, a 4-mirror system. This is a 4-mirror system. You can see the same thing. We have to do all the calibration and also alignments, and also look at the reference plane here. We have to the two type of measurements. One is so-called the natural TRL measurement for the TRL calibration for the measurement setup, and also the so-called the reference measurement. Difference plan based measurement system for the parametric extractions, okay, for our material on the test. So so this is we have to also look at system link. As I said, we want to have the optic path as low as the optic path loss as low as possible. So for this, the entire system measurement of interest, band frequency of interest, we look at the insertion loss from port to port, about 1.5 dB loss. Okay, so that's pretty good for 2-mirror system. 4-mirror system roughly are doubled, not really doubled, but about doubled. Okay, so it's well, it's a good system. It's a good system. Okay. Okay. Oh, by the way, if you look at this, the contribution of the humidity, even temperature actually put together actually change a little bit here. So that's very delicate. I said 180 gigahertz band, 185 roughly, 183, 83 gigahertz frequency range. You have to be careful. Okay, this frequency range, measurement can be strongly, significantly affected by this the variation in humidity and temperature, particularly for if you want to extract the accurately loss tangent of this frequency range. So that's show again this measurement setup how we have to guarantee the accuracy in the system. So so this is in our system here we use 4-inch square PCB substrates, some from largest companies, and also of course we remove the double-sided copper. You coated the double side. We remove both sides, and make sure that we can use also high quality by the considering also surface roughness aspect. Okay, so we use a step profiler to measure surface roughness, And so this gave us a very good insurance about the quality of measurements. And also we developed technique to do so-called Allen deviation tracking, okay? And Allen deviation tracking means that we set up a time frame and let the measurement running and look at the statistic data and to look at the deviation values. Okay, this deviation value come from this statistic Allen formula, and this gave us the certain kind of the so-called insurance. This particular for the high precision measurements. Usually this for the nuclear clocks, but the nuclear clock over the time we talk about years. What the deviations in the picoseconds or those kind of values. But here we use Allen deviation, talk about the how many seconds about this the measurement values variation. Okay, so yeah. So this is the measurement results port to port from S parameter value. Of course, you cannot see anything here from the you look at this spikes here, so on and so on. But through the parametric extraction technique we developed, we are able to see clearly the real permittivity, real part of the permittivity of these silicon wafers. Okay, these are thick wafers for 2-mirror system, 4-mirror system measurements. You can see actually they agree pretty well, and actually we know roughly values about 11.6 to 8 values, depending the density of silicons. Okay, you have high quality silicon or highly resistive silicon. In this case, you end up with slight different values, but about 11.67 values actually give us very good satisfaction. Okay, so this is 2-mirror, 4-mirror system results. And through the this gave us the also the the different silicon Rogers substrate values. You can see Rogers substrate values. Okay, RT values. Okay, about 13.5 here, and also another values here. Some variation over at the border frequency range here. Okay, this of course this is something a little bit because calibration or the measurement setup itself, which is not really valid over this frequency range. Okay, so actually give us quite stable values on the real part of the complex permittivities. Okay, so we are very satisfied with those results. And same time we look at the loss tangent. Okay, as I said, the loss tangent should be the measured result should be larger than the loss tangent resolutions. So this gives us right away values. For example, loss tangent value here give us this gives us a very good satisfaction. Okay, for example, this satisfaction results silicon larger thicker the silicon wafers give us very good results of this loss tangent. All this value, but for this Rogers substrate, the thin substrates, usually value is not very good. Loss tangent value is not good. So in actually to some extent for thicker substrates, the loss tangent is difficult to measure. Okay, and so this is why loss tangent value here is a little bit frustrated. It's actually it's a strong variation over I would say over the frequency range of interest. And so this is give you different substrate measurement results. I will not go through detail of that. All these results are based on the size of 4 by 4 inches, and the wafer is a 4-inch silicon wafer for thin substrates, and you can see thickness of values here, and also this is extracted parameter values, complex permittivity. Oh, actually, no, complex permittivity. This real parts, imaginary part, which is in terms of loss tangent values here. Okay, so this is 10 minus 4 values. Okay, so it's so uncertainty is given here. We can see minimum. Actually, the loss tangent resolution value is here. So based on this value, you can see how accurate you can get. So for example, for thicker silicon wafers, you can see you can guarantee you can have very good loss tangent accuracy. Okay, so actually we are more interested in loss tangent than the real parts, because real parts we have pretty good values obtained through this quasi-optical measurements here. So let me go quickly quasi-optical lens measurement system because time. We develop also this the measurement, the lens measurement system through this the Gaussian beams. But the Gaussian beam here uses rectangular horn antenna. Of course, here is an approximate Gaussian beams, but it's a pretty good values we can get because this planar convex lens actually give us a very good conversion from this Gaussian beam to the planar waves. Okay, this is a measurement setup we developed for the D bands. Okay, I will not go through and also G bands. So I will not go through this. This also we developed this the single slab multi-reflection models for the same technique. And also for this single slab, actually, you can see that how we can create this, because based on those multi-reflection models, we develop transmission and reflection equations. And actually, these equations, which are analytical, which allows us to extract the real part, imaginary part of this the values. Okay, I will go through I will not do show you these equations here, but I'll show you that the measurement results. You can see real parts, imaginary parts in terms of loss tangent. Actually, value is pretty good. There's some, uncertainty over certain frequency range, but it's still acceptable for our measurements. And the real part value is pretty good. And so this thing, one of the interesting things that for this particular technique, for thin and thick substrates, they are quite consistent in terms of values. But of course, we cannot see that the loss tangent value is really good or not, because right now scaling is quite large here. So, and so real parts, imaginary part, this is some, okay, this is real part value of this based on this lens-based measurements. But at the same time, we look at the lens measurements actually give us some interesting. If you sample a little bit rotated or the turned it, okay, turn a little bit, let's say inclined, for example, okay, we can still make a good measurement. For example, in this case, the rotation or the rotation angle is up to 5 degrees. We can see the measurement, the result still remain quite constant. Okay, so over the frequency interest. Okay, this is D bands. So we feel that this is very robust values, which regarding the some kind of sample is not very well placed. Okay, so for example, in this case, measurements still give you very nice results. So at the same time, if your input values, input power is not high enough, and you can how much the measurements, we talk about dynamic range. Okay, so the dynamic range, how good dynamic ranges are, we can get here for the measurements. In this case, we use absorbent. Absorbent gave roughly 60 dB at 180 gigahertz. The attenuations. So in this case, we see that the very weak power come out of this system, and the goes through the sample of under test. And of course, in this case, even that case, we can still get pretty good, decent results. So it's a very satisfactory. I said that is, so that means that the system dynamic range, thanks to the VNA or PNA, we are able to achieve very good the measurement results. So that's again, I said, compared to the traditional time domain spectroscopy, dynamic range based on the VNA PNA is really great. So conclusion, we have developed two set systems actually, in our laboratory, both based on parabolic and the four-parabolic mirror system. Actually, we will also spend time to investigate those ellipticoidal system. And that system actually gave us a little bit of troubles, based on the theoretical analysis. But the parabolic system definitely gave us a very good options. And we have shown that the system should satisfy really the frequency independent optical path conditions. And also we have to design very high quality Gaussian beam launching system based on corrugated horn here. And of course, we, in particular in this work, we developed very good, well, I would say the very accurate loss tangent, prediction theory based on the loss tangent resolution formula. This gave us certain assurance regarding the measurements for the low loss materials. At the same time, we have shown that through the measurement simulated results, and we've seen that the system is very robust. And actually, we can see that also the quasi-optical mirror system, quasi-optical lens system, both provide very good accurate results, and also under the very dynamic range, the environment. So, so this system can be, of course, extend to the higher terahertz frequency bands. So that's the my talk. So thank you very much for your time, and I will be very happy to listen to any question you may have here.
Thank you, Professor Keiru. It was a very interesting topic, very informative. Thank you for your time. We got a couple of questions in chat box, starting from Naveen. The first question is, with the recent supply chain issues of semiconductors, what other popular materials can be explored for terahertz component design?
Well, I can tell you recently, I was in a European Microwave Conference. Our colleague from Georgia Tech brought some interesting information about the new so-called flexible substrates, which is actually very low loss, extreme low loss. The microwave loss is very low, optical loss is very low, but we don't know the terahertz loss yet. So that's interesting to know. This material actually right now is being developed by DuPont, by the Corning company, but I don't know exactly. It's still in the research or the commercial stage or not. But there are lots of interesting materials. For example, classical material like silicon, the bulky silicon or highly resistive silicon, actually provide a very low loss at terahertz. But the problem is that you see any materials were subject to certain resonance absorptions. This is very natural. For example, we see that the silicon materials at the low frequency, you have sometimes you have very high loss for microwave, okay? But the optic frequency is extremely low. So somehow the frequency goes up, the loss goes up eventually, but it will drop down somehow. So we don't know this happened at terahertz frequency range or not. So this is why I say that this, which means that which material will be great at terahertz, we need to really investigate through the measurement to see the terahertz. So it's difficult to predict what new materials, better material at terahertz frequency range. So so with good measurement technique as we developed, I think we should be able to tell people which one is better. So that's the thing, yes.
Thank you, Professor. The next question is, how do you extract the on wafer, I hope I'm spelling this correct, on wafer loss tangent, since the radiation loss and metal conductor loss are very challenging to determine at high frequencies? Yeah.
Okay, of course, here what we developed here is only actually only useful for the material. Okay, it's not for metal. Metal actually metal loss. It's well, usually we talk about conductivity values here. Usually if you talk about the metal actually at terahertz, it's not really the well, there are two aspects. First of all, the intrinsic conductivity. Okay. Which means that so the conductivity here, at least over this very large frequency range, is a constant value, has been considered as constant values. Second is the surface roughness. Not only just the dielectric material have surface roughness issue, but also the conductors have surface roughness issue because of the fabrication process. Okay, so the surface roughness issue is really killer for many waveguide-based quasi-optic system. Oh, I'm sorry, waveguide solutions, okay, not quasi-optic. So compared to quasi-optic, waveguide solutions actually has a lot of problem because of loss, surface roughness loss. You need a very high precision mechanical processing to do to create an excellent surface roughness, and also it's difficult to do. Okay, and so the so that's why the waveguide-based the two-port measurements can be useful for low terahertz frequency range, such as D bands, G bands, such as 140, 200 something. But it's beyond 300 gigahertz is very difficult to do, okay? Because the waveguide section becomes smaller, and also the surface roughness become much more pronounced, okay? So as the frequency goes up, yes.
Great, thanks. I guess next question is kind of related to the answer you gave. I'm just gonna ask for your confirmation. What is the effect of surface roughness in your dielectric substrate measurement? Is that the same question?
Yeah. Okay, no, that's a slightly different story. Okay, I think that's okay. All those questions are great questions actually. So the surface roughness will create uncertainty in the measurements, particularly in the I would say in both dielectric measurements and all the real parts and imaginary part. Why is uncertainty issue? Because consider if you have the very good, high quality dielectric materials, but you have the very small, you know, if you have the surface roughness, this surface roughness can be considered as the additional layers, additional dielectric layers. It's like you have the, if you look at the entire single slab structures, you can consider as the 3-layer structures. You have the core perfect dielectric layers. Then you have the very thin attached 2 layers. So in this sense that you consider actually it's a 3-layer structures. That is 2-layer additional layers definitely will give you uncertainty in the measurements. So which means in a rigorous sense, you need to develop 3-layer multi-layer formula to do multi-layer formula, multi-reflection models to do some analytical analysis. Of course, it becomes much more involved, much more complicated. And in this case, yes, I think that's this thin layers contribute to uncertainty in the measurements. Yes, so that's why we had to avoid that.
Thank you, Professor. Next question is, any suggestion about characterizing wafers with multiple layers, like GaN wafer with multiple layers of silicon oxide?
Multiple wafer layer. What multiple?
It was like I'm reading it. It was multiple. Any suggestion about characterizing wafers with multiple layers? For example, GaN wafer with multiple layers of silicon oxide.
Oh, you mean you have multi-layer structures, multi-layer involved?
That sounds like that.
Okay. I think yeah, multiple layer is definitely important. For example, we have the if you want to measure the certain materials, maybe you need to develop a test bed with a specific design the holder. Okay, holder. The holder actually create additional layers, 2 layers. So in this case, you have 3-layer structures. Yes, multiple layer, as long as those 3-layer or 4-layer, 5 layers are well defined with well-conditioned thickness. In that case, the multiple reflection models can be used in a very straightforward way. Okay, there's no difficulty to do that. Formulation can be developed. Of course, need to be long, lengthy, I would say lengthy mathematical formula. Okay, but it's still doable. And I don't think there's a problem for that. But the only issue related to the final formulation maybe is not analytical. Maybe you end up with the numerical results. Yes, it can be done, and so we should be able to do that but we test our system without use complicated formula. But of course, multiple formulas actually has been derived in our laboratory. We have done that for 3 layers, 4 layers, this kind of things. Yeah.
Thank you, Professor, for taking time in answering questions. We got a few more questions.
Yeah.
Is it the right assumption that the parabolic mirrors should be placed at the far field of the horns? What is the range of D1 in your testbed block diagram?
Yes. Well, of course, for the Gaussian beam, in this case, you need to consider, of course, in our measurement setup is a far field because we talk about the terahertz, so the wavelength is very short. So if you look at our system here, we talk about the few centimeter far away from the horns. Yes, that's the far field. Okay, in our measurement conditions. So which means that the robotized system measure this Gaussian beam actually the far field. Yes, but the good thing about that this horn itself actually, when you look into the launch of the beam, the Gaussian beam actually this horn itself actually, well, if you look into that, this create the beam itself, it's a planar wave. Okay, so you don't need to really consider when you have the planar wave, you don't have really the far field, the near field issue here. The only far field issue is when you have the horn, which is for example traditional horn, you create spherical waves. This how the spherical wave can be converted into the planar wave. Of course, you can do that through long distance or far field measurements, or you can do using lens conversions. That's why we did. Okay, so you can see that we use planar convex the lens to do the job there. So yes, so a certain horn actually can create a natural planar wave if the design properly, but of course not always the case here. So yeah.
Thank you, Professor. The next question, first Milad says hello.
Okay.
And the question, I'm going to split this question to two questions. I feel it can be two questions. Is it possible to test the sample in the near field of two WR antennas without employing off-axis parabolic mirrors, assuming that the beam spot interacts with the sample in a Cauchy plane wave?
Well, yes or no? I would say this way. Yes is because as long as you can formulate in a rigorous way electromagnetic field equations, wave equations, for the near field interaction between the materials and your horns, which means you have to formulate the interactions in a very rigorous way, a full wave way. And then in this case, of course, all those material parameters will become part of your equations. Your equation must be nonlinear, all the nonlinear term involved, which means it's not explicit, it's not the easy inversion problem. Okay, so it's a much more involved. So as long as you can do that formula, and as long as you can relate to that formula to the measurement conditions, which means input S parameters, the transmission receiving S21, okay? So if you can measure S11, S21 parameters, in that case, yes, you should be able to do that. But the calculation will be much more complicated. And also, most likely, the measurement is a narrow band. It cannot be made for broadband. As I said, the optical paths, okay, need to be frequency independent. Okay, so cannot be made for broadband, and also the measurement is so complicated. You cannot make a so-called analytical formulation to extract the parameters, and even you cannot even do the sample analysis. So I will not go for that, I would say. So this, yeah, theoretically yes, practically not preferred. Okay, so yeah.
The question is being continued with this phrase. And what about the extraction parameter for plane wave fields regarding this scenario?
Okay, the planar wave is actually because you're not clearly because planar wave means that you have only the electrical magnetic fields components on the transverse sections, not in the propagation directions. Okay, in that case, so the formulation is very simple, and also you can use easy model to do the the reflection transmissions. Okay, But if you have this kind of near fields, your modes actually is hybrid. The electrical field, the magnetic fields actually could be polarized in arbitrary directions, depending how your material interacts with your fields. So you cannot have analytical equation for the model. Okay, model is very complicated, and so that's why you cannot make the because all we want to have is a model which allows us to extract the complex permittivity, real part, imaginary part. Of course, we usually describe the imaginary part by the loss tangent. Okay, so in this case, that's the key. So we must all the measurement technique. All we want is to have the very simple model to make a very quick parametric extractions. In some cases, we want to have the very good real-time parametric extractions. Okay, particularly for imaging, for example. Okay, so because you're moving around, in that case, you need to do that. And so system doesn't allows us to spend a few hours to make parametric extractions. Okay, we need to have a quick real-time job. Okay, so yeah.
Thank you, Professor. The next question. So we are getting question. I hope, Professor, you have time.
Yeah, sure.
Thank you so much.
I would be very happy to answer any question you have. Yes.
Thank you. Next question that sounds like the audience came across to a challenge. So I'm reading the questions. Bahar says, I'm working on dielectric constant and loss tangent detection using resonator structures in the microwave region. My simulation and measurement results are not compatible in terms of amplitude. Therefore, I cannot accurately determine the loss tangent with the equation I obtained from the simulation data using curve fitting. Is there any solution you can suggest me?
Okay, first of all, the resonance technique usually measures the low loss materials. Okay, if you have a high loss material, don't use the resonance technique. Okay, that's because so that's why we use a transmission technique combined with the resonance technique, because resonance technique gives you discrete frequency points. Okay, but at least use as a reference to compare with our transmission measurements. Okay, or the free space propagation, quasi-optical, whatever. But if you're the resonance technique, the problem is that because of resonance, particularly for low loss materials, you have high Q resonance. In that case, small variation in terms of the cavity design, or small the cavity tolerance, for example, mechanical tolerance, could change the values. Okay, so there's some fundamental issue. For example, if you have very high Q resonance, very low loss materials, theoretically speaking, yes, you can get a very nice formula to extract the loss tangent values. But practically, because you have high Q, the cavity structures, so a small, let's say, small variation of your geometrical dimensions, delta, okay, add one delta here, then right away you're changing your frequency, resonance frequency. You shift your resonance frequency, you shift everything, because for your given frequency, maybe you see nothing there. So that's trouble. So which means you have to consider tolerance, and tolerance is a big issue. So for most of the cavity structures, I would say people usually used for extreme low frequency. Extreme low frequency. Don't use for extremely high frequency measurements, because of tolerance kill your measurement system. So that's my suggestions, depending on your frequency range. I don't know what frequency you talk about here. Yeah.
Thank you, Professor. Next question comes from Anamia. How to characterize very thin quartz substrate at 345 gigahertz?
You mean the very thin substrates?
Yes.
Right? Yes, very thin substrates. Actually, now we okay. For the mirror, for the four-mirror system, we see clearly that we have difficulty, uncertainty issue because of the loss tangent resolution. Okay, but based on the two-mirror system, very high quality planar wave generation between two mirrors, we are able to still to do the high quality the extremely thin film, except because of the thin film, if the loss is very low, definitely if the loss is very low, you create uncertainty, which means, the certainty is come from there. So the best way is that the to be able to do the the thin film. So it would be better to analyze the thin film inference. I think for us, we will suggest using two mirror system because it's at a plane wave. Second thing, another thing that we will use both thick film and thin film together, which means the thick film give you a good reference about the loss tangent and the values of the permittivity, because we know the accuracy, we know the stability, of course, thanks to the loss tangent resolution analysis. Then from there, we'll be able to predict, at least through the two mirror system, to extract the thin film. Yes, a thin film is difficult. Yes, it's a very difficult thing to do. And actually, another thing we can do also using the so-called if you have the 2 or 3 thin film, we use cascaded, in this case. But of course, it involves more analysis. Okay.
Thank you, Professor. Next question comes from Amir Hossein. Thanks, Professor Wu. It was very interesting presentation. In a multi-layer scenario, how can we make sure the layers are attached without any air gaps? Of course, these air gaps will make errors in our measurements. Is there any setup or methodology developed in lab?
Yeah, this is well, excellent questions. At the same time, this is difficult questions because this involves the fabrication, the mechanical setup, different things there. It's not longer just the theoretical aspect or even our own test beds development. Well, the air gap is definitely is a killing factors for many measurements. Okay, not only just for our measurement, but also even for circuits. For example, if you have multi-layer circuits, you have the air gap or even small gap there. You design something, but you got something different. Okay, so maybe in the end. So so in that case, what I suggest is this. I think the best way is because in most air gap, we can use the vacuum process. If you create a multi-layer structures, okay, we use a compression process. It doesn't give you really the best results, but the compression, but at the same time, you can extract all the airs using the vacuum. Then in that case, you're using, I don't know, maybe thermal bonding, whatever layer technique. Maybe there's some potential solution there, but actually this is part of the fabrication in the LTCC and other fabrication technique there. But I don't know. Honestly speaking, I don't know whether for our own measurement technique we do have any good solutions there. Honestly speaking, I don't think that we have this good solution. Yeah.
Yeah, I think Amir Hossein is from Polygrams. So the final question is from Mohammed Taher. Hello, everyone. Thanks for your interesting presentation, Dr. Wu. I have a question about material characterization. As I found in papers, for instance, to determine the thickness of a sample with terahertz time domain spectroscopy, actually it evaluates with a known refractive index. So what about unknown material? How we can characterize an unknown material? Is that possible?
I didn't. Could you repeat the question again?
Yeah. As I found in papers, for instance, to determine the thickness of a sample with terahertz time domain spectroscopy, actually it evaluates with a known refractive index. So what about unknown material? How we can characterize an unknown material? Is that possible?
Yes, I think so. I can tell you why. I can tell you why, right away. Yes, you can do it. Okay. Why I can do it? Let me tell you why. Actually, if you add the one additional parameter such as the thickness, okay. So in the equation you have D, okay. You have I said or T, whatever thickness or D, whatever. So the thickness parameters actually will be involved in the equations, but in that case you need more. You need more equations. Okay, you need more set of equations. For example, I said in the discussion presentation here, you have the transmission, okay, equations. Also, you have reflection equations. But actually, so far we haven't considered this permeability issue. We could just consider permittivity, okay, which means magnetic, no magnetic materials, only electrical materials. So in that case, we only consider transmission equations. But if you consider the additional unknown parameters such as the thickness, in that case, you can consider, of course, the thickness cannot be very large. Okay, as I say, roughly, it can be still accommodated in the measurement system. Okay, in that case, as long as they satisfy the measurement system requirement for any thickness, in that case, we should be able to use this both transmission and reflections to extract the thickness. Yes, I think so. But only issue that the thickness, if you look at physical thickness, you can measure by the hand. Okay, you can use the scalar. Okay, you can use the anything to optically or just do the mechanically. You can measure. But of course, if you do the remotely, yes, I think your question definitely is an interesting questions. If we can do the for example, if you through the certain kind of the long distance, other side you have receiver. This side has this transmitter. In that case, you consider as a quasi-optical measurement. But in that case, yes, we should be able to measure the thickness. Yes, that's a very interesting questions. But we haven't done yet. Nobody has done yet, at least for us at least.
Thank you, Professor Kebu. That was the last question. So thank you everyone for asking questions. Indeed, Professor Kebu took extra time to answer your questions, and we truly appreciate his time. So Professor Kebu, it was really a great pleasure to have you in this event. Unfortunately, Dr. Gunesh had a commitment to make for class, so she asked me to thank you on behalf of her as well, and on behalf of IEEE Young Professionals Montreal and all co-hosts. I really appreciate your time dedicated for this interesting event.
Thank you.
And we very much look forward to see you in person, Professor Kebu, one day. I guess like COVID is almost finished, and we very much look forward to at least see you in person.
Sure, we'll do that. I'm sure next time I can talk about the wireless technology. Actually, that's will be the will be our mainstream research. This material stuff is actually our first early research for our the Terahertz system development. That's we developed this technique. But actually, our mainstream research related to the wireless technology, transceivers, and those kind of things. Yeah, definitely. I haven't discussed today our research topics, but I'm sure we should be able to one day have a chance to talk about that. Yes.
Yeah, I'm sure a lot of amazing stuff is running in Polygram Center, led by Professor Kebu. Everybody is aware of your solid and strong contributions you made to the community. So officially, we reached out the end of the event. Thank you everybody for your attendance. And once again, thank you, Professor Kebu, for your time dedicated for this event. We very much look forward to see you again. Thank you.
Well, thank you very much, Mansoor, and hopefully we'll see you soon too in person. Yes.
Yeah, we have a lot of events scheduled. You know that. I will reach out again.
Okay, great.
Thank you so much, and have a good day.
Okay, you too. Okay, have a great day.
Bye.
Bye-bye.